Okay, and we're back after the break, and we're ready for the last session for today. It will be last presentation session also. It will be Machine Intelligence session 3. Papers in this session will be focusing on a warning system for electric grid, electric skin, and microbial colon detection, which, as you may expect, brings me to the last riddle today. Why are bacteria bad at math? Because they multiply by dividing. Yeah, so we are ready to start the session now. The chair for this last session will be Salih Sarp from the Virginia Commonwealth University. Hi, Salih.
Hi, Professor Biere.
Hi, how are you?
I'm doing fine. Yeah, it's wonderful conference.
Oh, okay, great. It's nice to have you here for this session. Okay, so I will pass the voice to you. The floor is yours.
Yeah, thank you for Professor Biere, and thank you everybody for joining us in this session. I'm very excited that this will be one of my early experiences of serving in a conference. And in this session, we have 5 beautiful studies that most of them benefits from the use of AI in different areas. After presentation of each paper, there will be a 5-minute Q&A session. Before jumping to the presentations, first of all, I would like to apologize for my bad pronunciation of your names. Secondly, all authors of the given paper, please switch on your cameras. And lastly, please feel free to ask questions on the chat window. I will ask these at the end of each session, each presentation. Now we have Sylvia and her colleagues for the presentation of deep neural networks approach to microbial colony detection, a comparative analysis.
Welcome, everybody. My name is Sylvia Mikrofska, and today I will be talking about deep neural networks approach to microbial colony detection and counting. So, let me introduce myself. I am a PhD student in physics at Wrocław University of Science and Technology in Poland, and I am investigating their novel nonlinear optical phenomena that occur in multimode optical fibers. Professionally, currently I work at AI Sweden, where I am a member of program A4AI. This is an exclusive program created by AI Sweden together with partners. In this program, I have the opportunity to work on concrete applied data and AI problems in 3 different application areas, mainly in healthcare. But today's presentation is about my work at Neurosys, where I was conducting research on computer vision by designing and developing deep learning algorithm for detecting, counting, and classifying microbial colonies grown on Petri dish. The ability to automatically and accurately detect, localize and classify bacterial and fungal colonies grown on solid agar is of wide interest in microbiology, biochemistry, food industry, or medicine. An accurate and fast procedure for determining the number and the type of microbial colony grown on Petri dish is crucial for economical reasons. Industrial testing often relies on proper determination of colony-forming units. Conventionally, the analysis of samples is performed by training professional, and this is doing manually, even though it is a time-consuming and error-prone process. To avoid this issue, we can apply some automated methodology based on artificial intelligence. And in our experiments, we are using higher resolution subset of annotated germs for automated recognition, agar in short, database. The dataset is an image database of microbial colonies cultured on agar plate, and the whole database consists of 18,000 photos of 5 different microorganisms taken under diverse lighting conditions with 2 different cameras. All images are classified into countable, uncountable, and empty, with the former being labeled by microbiologists with colony location and species identification. And this gives in total around 340,000 colonies. We here used higher resolution subset. So this subset consists of around 7,000 annotated Petri dish photos with 5 microbial classes. And in this work, we rely on detection-based object counting. So the implementation of detection-based object counting can be done using some state-of-the-art object detection methods, or even some older, like faster RCNN or YOLO, where the model detects the target objects in the image. After all, we can assume the number of the detected objects, so the number of the bounding box, to obtain the count. And in our studies, we compare the results of microbe colony counting using selected detectors belonging to 3 different classes of neural network architectures, namely 2-stage, 1-stage, and transformer-based models. Example of images of microbial species and achieved prediction for a selected sample are presented on the slide. The whole image of the Petri dish presents ground truth annotation, while the white dashed rectangle indicates the region chosen for visualization of prediction. Red rectangles mark Pseudomonas aeruginosa species, which form the big colonies with blurred edges. And here we can also observe that this type of the microbe can form 2 different colonies depending on the agar substrate. So this ground truth is divided into the half. And also in the ground truth, we have some small black rectangle. This is the contamination, so microorganism not intentionally cultured. In the prediction, we do not have this type of class. We have just some species. So we can observe green bounding box. This is for the Candida albicans. And this organism form small, round, and dense colonies. And navy for Staphylococcus aureus with medium colonies. We can observe that obtained results for all networks are visually similar. However, labeled small contamination is not perceived by all models. And 2-stage detectors have a tendency to produce some excessive predictions. Going into details with our results, the evaluation metric for colony detection was based on the mean average precision previously established for COCO competition. So here it is average over all classes and intersection over union range. When it comes to counting, the recognition of microbes is crucial, but the exactness of their localization is of secondary importance. Here we use symmetric mean absolute percentage error to evaluate the counting quality. Additionally, we compared the performance of the selected models using architecture type and size and inference time. These parameters are crucial if it comes to industrial application. The most efficient results in terms of accuracy and inference speed were achieved for YOLO version 4 architecture. On the other hand, transformer-based architecture presents slightly worse performance. So, summing up our results, I can say that we proved the great potential of deep learning methods to automate the process of microbes localization and classification based on Petri dishes images. Moreover, the agar dataset used in this study is the first publicly available dataset of this kind and size, serving for future development of machine learning models. We examined here a few deep learning-based architecture from 3 different neural network classes. Overall, the best results were obtained for the YOLO model, version 4, where the predicted count of microbial colonies is the closest to the ground truth in range from 1 to 50 instances. This is the most operable scope for industrial application. However, in the identification of abnormal colonies grown in Petri dish can be difficult even for a trained specialist. Overlooked microbes were usually small and located at the edge of the Petri dish. Usually 10% error is an acceptable range for manual labeling, and it is worth pointing out that AI-assisted models can't make prediction even for overcrowded dishes, which is a big advantage of this type of the technology. And at the end of my speech, I want to acknowledge financial support from the European Union funds. The AGAR project was implemented as the part of National Center for Research and Development Fast Track in the Neurosys company, and also with the support of our interns during the summer. Thank you for your attention.
Thank you for the good presentation. Now I would like to ask authors to present themselves. Yeah.
Okay, so welcome everybody. My name is Sylvia Mikrofska, and I was presenting on the recording, which was shown. I see that my colleagues are here. I don't know if they want to introduce themselves also.
Hello, my name is Jarek, and I also take part in this project.
Meeting you. And feel free to ask questions in the chat window. Since there is no questions in the chat, I would like to see the Q&A session with some questions regarding the preprocessing and the data set. And did you use any image preprocessing, such as removal of writings in the image data set?
Okay, so if it comes to image processing, it wasn't like that. The images are very, very high resolution. So we have to divide them into small pieces. We call them patches. And the patches just were input to our networks. Because we can also make the images smaller. We take this kind of the tests, but the microbial colonies are really, very small. So in case of resizing, the detectors cannot detect them well. So the first thing here was just this approach, this pipeline to divide images into patches. And we try to do this in that manner that to be sure that on patches we have some really objects. So we have some microbial colonies. And at the end we add some parts of image which are empty.
Great. And you fed the, to test the model, you fed with the whole image?
No, we also fed in the testing setting, we also divide the whole Petri dish into the patches, but with some overlapping. So we have more patches in that case.
Okay, all right. Also, I have a follow-up question about the ground truths. The ground truth, is it done by you or previously available? And also, AGAR dataset is available. Is it available to the public?
Yes, AGAR dataset is available to the public. I can, after this speech, put the link in the chat. And this is for non-commercial research. And coming back to the first question, could you repeat that, please? It was something with the annotation, I think.
Yeah, about the ground truth, is it done by you or it is previously available?
Okay, so about the ground truth, all that data set was collected by us during the whole project. And we have collaboration with University of Wrocław. So the annotation was made by them, by professional microbiologists.
Great. Yeah, use of transformers with ResNet and FastRCN is also interesting. A very impressive study. Thank you.
Thank you.
Now we have Christoph and his colleague for the presentation, Low Voltage Warning System for Standalone Metering Station using AI on the Edge.
Good afternoon. My name is Krzysztof Turhan and I work at IHP. IHP is a research institute in Frankfurt Oder in Germany. The topic of my today's presentation is low voltage warning system for standalone metering station using AI on the edge. At the beginning, I will mention for what purpose the application described in the paper was created. Then I will introduce the general concept behind this work, and then I will give you some more specific information about the issues that were solved. I will provide the information on time series forecasting method, which is called Holt linear trend method. And I will conclude my talk with current status and next steps. A year ago at the MIDI conference, I talked about the framework to help create AI applications for embedded devices. This framework is designed to help find a solution based on the presented problem and the input data. Using different approaches, we can define different solutions to the same problem. Solutions can be like low power, high power with lower or higher accuracy. The choice of the solutions depends on hardware resources, and this is very often the most important factor. The work I present today deals with an example use case scenario for the framework. In an AI-based application, the idea is to choose the best possible method based on the needs. The problem we are facing was related to the metering station, or more specifically, the power supply part of the station. Our station is powered by batteries that are charged by solar charger connected to the photovoltaic panel, and all electrical parameters are measured by a 3-channel DC meter. This DC meter is a board based on microcontroller from the 16-bit family, exactly MSP 430 family. Our main task was to implement an application to warn in case the battery cannot provide enough power soon. The application should use an AI solution for that. However, we had to take into account some hardware limitations. First hardware limitation is low computing power on the microcontroller. And second is possible interruptions in the internet connection. 3-channel meter collects a lot of measurement data, while the solution doesn't have to be based on all of them. It all depends on the computing power of the microcontroller. And in this case, we were dealing with a 16-bit microcontroller, so it was important to choose as simple artificial intelligence method as possible. As can be seen in this figure, the data that has been collected are nothing more than time series. And to simplify the model as much as possible, we choose only the battery voltage data. Next, we looked for an algorithm to predict next values based on historical battery voltage data. There are many methods of prediction in time series, but their use depends mainly on the shape of the time series we have. we decided to use Holt's linear trend method. Any dataset that follows a trend can use this method for forecasting. Thanks to the method, it is possible to predict future value using a linear trend. Holt's method has three separate equations that work together to generate a final forecast. The first equation is a smoothing equation. It adjusts the last smoothed value to the trend of the last period. The trend is updated over time using equation 2, and it involves determining the difference between the last two smoothed values. The third equation is used for forecasting. Here is an algorithm. The microcontroller task is to predict the battery voltage value for the next day based on the data from the 5 preceding days. In order to do this, the data must be prepared in advance. Each measurement is taken every 10 minutes and the predicted values must be daily values. So in order to standardize the data with those that must be predicted, it needs to be averaged beforehand. The data is averaged every 12 hours, which gives 2 values per day. This data is then stored in an array with the size of 10 elements, and when this array is full, the first forecast of 2 12 hours values is made using the Holt's linear trend method. The value from the second forecast value is then checked. If this value is below the battery threshold, then a low battery warning is given. Each day, the 2 oldest elements are removed from the array to make space for the 2 new values. The data in the array is shifted, and the 2 new average values calculated from the current day are written to the array. This is followed by recalculation of the 2 forecast values for the following day. Then the algorithm is repeated over and over again. So this gives a daily value for voltage value forecast for the next day. We are currently in the process of testing our solution in natural setting. We previously performed tests under simulating conditions, and figure 3 shows the result of the test. We still have few more steps to do, and first step is estimation of algorithm precision and comparing with neural network based approaches. Then evaluation of microcontroller resource consumption for several approaches, and implementation of algorithms using all collected data. The whole idea of designing the low battery warning system based on artificial intelligence was to improve the operation of the entire metering station. By using a simple algorithm, we accomplished the goal with little cost in computing power. But the problem is abstracted very much. We will also compare the prediction with real-life long-term measurements. And that brings us to the end. I'd like to thank you for your time and attention today.
Thank you for the good presentation. I suppose authors couldn't connect to the conference for now. Hopefully we could meet with them at the breakout rooms. So, and yeah, I would like to stress that AI become more common and applied almost everywhere with the development of computing power and availability of the data. The idea behind this study is very unique. When I first hear this project, especially holds linear trend method, it is very simple but very powerful method and widely known smoothing model for forecasting data that has a trend, a gripping study. Thank you. Now I will get to the next presentation. Next one is from Jakub with test framework for collaborative robots graphene-based electronic skin.
My name is Jakub Murzaren, and I represent the research group from the Institute of Automatic Control and Robotics at Warsaw University of Technology. During MIDI Conference, I would like to present the test framework for collaborative robot graphene-based electronic skin. It is a part of a research pursued together with Jan Klimaszewski and Łukasz Gruszka. Recently, there have been growing expectations in robotics. Namely, robots should cooperate with people safely and intuitively, allowing for agile manipulation of different objects. Our research is concentrated on a touch sense, as it is one of the most natural ways of human interaction with the environment. With the sensor miniaturization and the new tactile technologies development, it is possible to create a full-body tactile electronic skin and use it in robotics. So, it is a novel research problem. How to properly implement the touch interface in the form of the flexible, dispersed electronic skin produced, for example, using graphene nano platelets. In our research group, with colleagues designing precise graphene-based sensors, we work on integrating the tactile interfaces with industrial robots. Our work aims to develop the hardware and software framework combined in a laboratory test stand, allowing for the functional tests of the newly developed graphene-based electronic skin or e-skin with the cobot. The collaborative robot should work closely with humans. The important issue in this context is to create a safe human-machine interaction. Therefore, it is important to detect human touch early and force the robot to work with the safe speed and force. So in the picture, there is presented the electronic skin layer and how it looks like. So it consists of a graphene-based force sensing resistors matrix made of two layers. So the first layer is so-called resistive layer. The second layer consists of three parts. So it consists of comp electrodes connected in columns here. Then we have the electric separators. So this is the second part of the second layer. And the third part are the paths connecting sensors in rows. That allows us to have the matrix detecting precisely where touch occurs and the pressure value of the touch. We have created a special software for hand touch visualization. In this picture, you can see the e-skin interface of the size of 16 rows and 32 columns matrix, allowing to detect the pressure from the hand presented in the A part. In the B part of this picture, you can see the pressure readouts for fingers detection. So here we can see the hand, and here we can see fingers, and we can also read the pressure from each finger. So in our test stand we have used the Es5 Robot developed by the Polish company Easy Robots. This is the robot that uses the Robot Operating System or ROS system, and its control system is based on this operating system. So it is the open source software platform very popular in robotics. The robot has 921 mm range and 5 kg payload, so it is not very big one, however very useful robot, and it is mainly used in the metalworking industry, for example for bending or palletizing or welding. The research we carried was based on the simulation in 3D visualization ROS application RVs, which provides a view of a robot model and the robot's environment. We also tested the electronic e-skin module with real Es5 Robot. Now I want to tell a little bit more about the software, especially the interface between the robot and the electronic skin module. So, first, the data exchange protocol was based on publishing and subscribing messages on topics provided by robot operating system. The ROS node was developed allowing for the measurements of e-skin sensors with 50 Hz frequency, sending the two-dimensional matrix of numbers corresponding to the pressure readouts from the module. Another ROS node associated with the robot control system was subscribing to the measurements node from the electronic skin and analyzing the obtained values. It was seeking the ones exceeding the fixed threshold. This node sent information into the robot control system to slow down the robot movements. So, during experiments, robot was moving along the experimental trajectory consisting of the sections of the straight lines, and two center point was moving with the maximum speed of 1 meter per second. In response to human contact with the electronic skin, the robot was forced to slow down to 250 mm per second, the speed required by guidelines in the industrial norm defining the collaborative robot reduced speed for the safe human-robot interaction. The research was divided into the following steps. The first, the initial research based on the simulation in RVs for fast development of electronic skin and interface and robot reaction. So here we observed the interaction, and it allowed us quickly to develop the proper interface first, and then also to develop the safe movements of the robot. Then, in the second stage, we integrated the electronic skin with the real robot to perform final tests. During tests, the module was separated physically from the robot. So, in this case, our prototype is not exactly placed on the robot as a skin, but works as a separate module. This picture shows our laboratory test stand. In the upper left corner, you can see the electronic skin software interface divided into columns and rows, and it shows the position of the touch and the pressure value. On the right hand side, you can see the robot arm. In the short movie next, you will see the robot operating at the maximum speed and slowing down when the human touch is detected. So the following figure presents the reaction times for pressure detection. With the dashed line, there is indicated the moment when the pressure is detected. So here is a dashed line. Then the dotted line shows the moment where the robot reacts by reducing the speed. Finally, with the dash and dot line, you can see when the safe speed is reached. So the following table gathers the time reactions in seconds for the pressure detection with electronic skin. First, the pressure is detected. Then, after that moment, the robot reacts in about half a second. Then the safe speed is reached by the robot in 1/3 of a second. So let's summarize the research. First, the functional tests on the laboratory stand showed that the robot could be forced to slow down in response to human contact with the electronic skin so it can move from the standard speed to the speed safer for human-robot interaction. Then, the presented test stand and framework can be used for further research of e-skin technology. Finally, in further work, we need to optimize the measurement and computational delays. Current reaction is a bit too slow for humans to work with robots equipped with the proposed e-skin comfortably. So human touch detection should be shortened to milliseconds. Finally, I would like to emphasize that the robot e-skin research is recently a very hot topic. Similar electronic skin interfaces can be useful in many different areas, as given in the picture. Our research group currently works with bioengineers from Warsaw University of Technology on electronic skin use in prosthetics. Thank you for your attention.
Thank you for the good presentation, Jakub. And I would like to ask authors to present themselves now.
Oh my God. I got problems. Okay. Yeah. Okay. You got me. Yes, I can answer your question. I got some problems with microphone, but now everything works properly.
All right. Could you present yourself first?
Yes.
All right. There is a question by Gabriela. She's asking, are the layers of e-skin inspired also by the natural skin layers? Is it in any way similar?
I think it's I can say like the how it works. It is a bit similar, but these are just a pressure sensors. So the way it was built is not inspired by biology, but the whole matrix is somehow inspired by biology. So how the layers are constructed is in fact the typical way we construct things. So it's not very nature inspired, I can say.
Right. I have a follow-up question. Does it differentiate a human touch with any other object touching?
No, it doesn't.
Okay. All right. All right. Thank you again for this wonderful study.
But
now,
I think, sorry, maybe I can answer a little bit more elaborate on this. So in fact, we can try to differentiate, but I think we can differentiate either by the detecting what is somehow touching. So we can, like, for example, detect the hand, or by the pressure. But, you know, like presumably we can say that something else, like a soft ball, for example, touches the robot, and the reaction will be the same.
And as far as I know, this is a test bed.
Yes, this is the test, yeah.
And is it planned to cover robots with e-skins in the future? The
Yes.
whole body or some parts?
That's also another good question. Probably in the beginning, because we are just in the preliminary stage of our research. In the beginning, we will be trying to cover only some little parts of the robot with this electronic skin. And we also currently are working on creating a soft skin. I mean, like the soft soft material that can be used to cover the robot. Because now, you know, it's just a matrix with the graphene-based sensors. And they are much like, it's a quite new technology, but we already know, and we have we are working with some scientists who can help us to cover something like, create something like a cloth that can be, for example, used as a part of the robot to be used as a skin. So then we can cover even the whole body of the robot.
Right. Also, for a future work, or I would like to ask about the delay you mentioned in the presentation. Is it mostly related to software issue or a device level issue? Could it be fixed within robot operating system, like increasing the frequency? It was 50 Hz, as I remember in the presentation.
Yes. Probably it won't be by fixing the frequency, because there are also many other elements like the servo mechanisms or cameras and so on that should be within the system. So the more or less we will be, probably it's more connected with ROS and with the software optimization. So probably our first work on this problem with the delay will be on the software optimization and algorithm optimization.
All right. Thank you again for this wonderful study. Thank you.
Okay, thank you.
Now, I would like to go on to the next presentation. Now, Fatih will present us the realization of real-time decision support system to reduce the risk of diseases caused by posture disorders among computer users.
Hello and welcome. This presentation is about the realization of a real-time decision support system to reduce the risk of diseases caused by posture disorders among computer users. These are the major parts of the paper. We will introduce you the content of the paper and techniques that we use, and we will talk about a bit methodology. Our R&D center. The company that we are working for is a software company in Istanbul, and at the same time it has a research lab that works on many fields of AI. This paper is one of computer vision research projects that we worked. Let's look at the paper in details. Let's give a brief information about the research. The time spent in front of the computer increased with the change of both remote working and education. Diseases caused by postural disorders continue to increase and decrease the quality of life and work efficiency. In order to prevent the diseases, we used pose estimation and we used open pose library. Pose estimation is made by processing the images taken from the computer's camera. Transfer learning technique used to open pose to get a base model. It is trained against MPII dataset again. Most of the studies use a top-down approach for detection and estimation. First, determines the people and detects smaller body parts and joints from the big picture of the person. Bottom-up approach in pose estimation. In this approach, all parts and joints of each individual in the image are identified firstly. Parts of different individuals are combined and grouped. This approach works slower than the top-down approach but gives more accurate results. In this study, a real-time decision support system application has been developed for computer users. In the open pose study, which has proven its success for the purpose, the pose estimation model was retained using the transfer learning technique utilizing the customized MPII human pose dataset. The data, which includes upper side of the body, are used from MPII dataset. Lower part of the body's labels are excluded from the dataset. This project can be run by built-in laptop camera. It has no cost, fixed focus, and can be used to supply 30 frames per second. NVIDIA Tesla T4 graphic card is used to train model. This card is specially designed for AI applications. However, it's not necessary to run the project. This study is based on OpenPose pre-trained model. MPII dataset is used to enrich OpenPose model. MPII human pose dataset contains approximately 25,000 images. It has more than 30,000 people and the dataset has tagged activities. Pose estimation is the task of using an ML model to estimate the pose of a person from an image or a video by estimating the spatial location of key body joints. Top-down approaches provide high accuracy for the one person. For many people, the accuracy is decreasing. Bottom-up approaches provides high accuracy and precision for one person and more than one person. Accuracy is the key point of our study, so this approach is decided. Transfer learning is a research problem in machine learning that focuses on storing knowledge gained while solving one problem and applying it to a different but related problem. For example, knowledge gained while learning to recognize cars could apply when trying to recognize tracks. OpenPose model is optimized using transfer learning techniques. Neuron count of the last of fully connected layers is decreased from 25 to 12. The OpenPose model already recognizes 25 body parts, so first two branches are frozen and weights are stored. Training is performed on last layers of the model that newly added, so we created the new model, the new improved model. The user interface has been designed to be used easily. It developed as a cross-platform environment. Controls and sensitivity can be adjusted through interface. Reference values and periods can be changed through the UI. Profiling is also possible to switch different conditions. This is a short video showing how the system works. The images reserved from the dataset for testing used to compare results of different models. The high-performance models are listed below. Models were compared with the proposed method in Table 1 with respect to accuracy and precision. Since the most important parameter for the applicability of the study is speed, the proposed method performed better than other methods. Health is one of the significant elements that reduce efficiency in organizations. In addition, one of the biggest expense items in most countries is healthcare. This study aimed to contribute to the country's economy by identifying situations that reduce working efficiency and quality of life. In order to achieve this aim, an optimized pose estimation model is proposed using the transfer learning technique. With the developed application, posture disorders analysis will be performed and health problems that may occur in the waist, neck, and joint regions will be prevented. Visual disturbances will be prevented by analyzing the distance to the monitor, working environment lighting, and usage time. With the help of the proposed model, the work environment will be analyzed dynamically to support a healthy working condition. Thank you for your attention.
Thank you for the good presentation, Fatih. And I would like to ask authors to present themselves. and I am one of them. Yep. Could you unmute yourself, Fatih?
Yes, I tried to open, but I had a little problem. It's okay for the moment, I think. My name is Fatih Balkı, one of authors of the study. It was a very good study, and we worked on that study as a team. It was a very good team collaboration. And we are in Istanbul. We are working for a research company in Istanbul that works on many fields of AI, as you saw in the presentation. And my colleagues are here, I think, but I couldn't see. If they're here, maybe they can want to say hello, but I think they couldn't connect, maybe. Okay.
Thank you. And yeah, I'm expecting any questions from the chat window.
Okay, if you have, maybe we can discuss about together.
Yes. And since there is no questions in the chat window, I would like to see a Q&A session with the following questions. And yeah, I can ask how many people was measured during the study? We see one person in the video. Is there any other people to validate the model?
We worked with several people that have several characteristics. Someone who has glasses, someone who doesn't have glasses, someone who is a man, someone who is a woman. We worked several people to issue accurate results.
Thank you. Thank you. And also, did you use any sensor other than camera for the study?
Yes. First time we used infrared sensor to measure the distance of the camera between the people and the computer, and we measured the real distance, and we calculated approximate distance using the points of the pose estimation. And we issued very accurate results, and then we prepared some measurements, so we used the calculations.
Thank you. Appreciate it. And yeah, with the ongoing pandemic, our working environment changed a lot. And similar studies arise to overcome some of the problems, and this is one of them. Now, I would like to move to the last presentation in this session. Now we will listen Paulina for the presentation of on two approaches to clustering of cross-sections of rotationally symmetric objects.
Ladies and gentlemen, it's my great pleasure to present at the MIDI conference. First and foremost, I would like to thank the organizing committee for giving me opportunity to give a talk. Today, I want to present my work done in collaboration with Agnieszka Kaliszewska and Monika Syga in the field of clustering of cross-sections of rotationally symmetric objects. The title is On Two Approaches to Clustering of Cross-Sections of Rotationally Symmetric Objects. Our contribution is devoted to clustering of 2D objects with respect to shape and size. The size can easily be quantified, whereas the formal quantified expression of shape is still the topic of current research. In order to obtain significant results of clustering, aside from the choice of the specific clustering algorithm, the following issues are of fundamental importance: the choice of suitable data representation and the definition of adequate similarity measure. The choice of data representation for the investigated dataset has a considerable impact on the possibility to achieve satisfying results. The experiments were performed on real-life archaeological data representing cross-sections of ceramic vases. Our entry data in the form of black and white images of a unified resolution. When the clustering archaeological ceramic data, one can hardly specify the number of clusters in advance, so we are bound to use algorithms which not to require the number of clusters to be predefined. The main difficulties in the selection of this test set are the numbers of data is small and correct classification is unknown and must be done by the expert. Here we show an example of dataset used in our experiment. The difference in shape are generally suitable. The clusters as presented here are based on experts' evaluation. We consider two types of shapes representation: contours and silhouettes. In contour-based approach, we extract the contour of the image, which is the boundary discrete curves, and next, the contour is placed in the coordinate system. In silhouette-based approach, starting from 2D image, the silhouette is transformed into a binary matrix. If the 2D images are cross-sections of 3D objects, by classifying those images, we obtain a classification of 3D objects. In the silhouette-based approach, we perform clustering based on similarity measures dedicated to binary data. Our selection of similarity measures for footer analysis was focused on the diversity. As a result, 5 measures were selected for footer analysis. Let X and Y binary matrices in the same sizes. D00 to D11 are the numbers of instances when combination of 0 and 1 in the same position in row and column is passed, respectively, and the definition is showed. Hamming distance focuses only on information about the difference between objects. Varies and Roger-Tanimoto distance analyzes the full spectrum of information on object similarities and differences. It was applied to nature cases, example maize genetic coefficients based on microsatellite markers or diversity in olives. The pattern difference and size difference distance measures the squares of information. In this approach, we represent shapes as matrices of pixels, to be clustered as binary matrices or, in some cases, as binary vectors. Process of preparing input data consists of 2 steps. First step relies on the analysis of the size of original input data. Size analysis is performed by Kamin's cluster algorithm. Second step is related to data transformation. We start with transforming every object to the chosen fixed size, which is related to resolution of provided objects. Next step is to create matrix representation of each object. The rows and columns of matrix represent pixels of objects. After data preparation, we perform clustering based on similarity measures dedicated to binary data. After calculating the similarity matrix, the effectiveness of each of the similarity measures was evaluated by the clustering method. The clustering is performed by the affinity propagation algorithm. An important feature of the proposed approach is that the clustering analysis is performed sequentially, first with respect to size and next with respect to shape. In the contour-based approach, objects to be clustered are discrete curves. We calculate distances between pairs of contours by using the formula SM, by using Procruster's measure and the dynamic time wrapping. It includes the scale component and can be adjusted through weights mi, lambda, and omega. We perform clustering by the standard hierarchical algorithm and generate the dendrogram. The average linkage is used to measure the distance between clusters. This contour-based approach is proposed in publication, a comprehensive study of clustering a class of 2D shapes by Agnieszka Kaliszewska and Monika Syga. An important feature of the contour-based approach is that the weights appearing in the definition of the similarity measures allow the simultaneous clustering with respect to size and shape. On the current slides, the results from all analyses are showed. It's worth to mention that the data we use comes from the field of archaeology. As there are no benchmarks for this kind of data, the data we used comes from archaeological publications. The publications on the clustering of archaeological vassals are scarce. Most of them I cited in our publication accompanying this conference. As in many cases of clustering, we face the lack of automated and semi-automated evaluation methods. Hence, for this investigation, we rely on the expert-based evaluation of clusters. The results are expressed by the percentages of correctly clustered elements. Based on the results, we feel confident to evaluate the performance of both approaches as acceptable, with the average scores for each method between 78 to 86%. Moreover, with few set-specific exceptions, the choice of the similarity measure in silhouette-based approach seems to have little impact on the resulting clusters. What is even more striking, also the applied orders of clustering, sequential or simultaneous, seem not to influence the clustering results in a decisive way. One should note here that the reported computation experiment is based on sets of medium sizes, around 30 to 40 elements. Some robustness of the results with respect sequential versus simultaneous approach could be implied by the fact that size and shape are the features of completely different natures. The size can easily be quantified, whereas the formal quantified expression of shape is still the topic of current research. In conclusion, both the contour and the silhouette-based approach are able to be applied to the clustering of 2D objects with respect to size and shape. Moreover, to the best of our knowledge, the silhouette-based approach has not been used in archaeological applications. Lastly, let me end by presenting some conclusions and questions to be addressed in the future. Our main conclusion from this study is that both approaches give satisfying results. We want to investigate the presented subject deeper to find more adequate ways for evaluating results. Also, we want to specify classes of problems for which each of the approach gives better results. Thank you for your attention.
Thank you for this wonderful presentation. Now I would like to ask authors to present themselves.
Okay, so nice to be here. As mentioned, I'm Paulina Baczyńska. I'm from researcher team, and in this team there are 3 people. As mentioned, Agnieszka Kaliszewska, Monika Syga, with such a big help from Professor Ewa Bednarczuk. We are working in Polish Academy of Science, and we are focused in applied machine learning, mathematical methods in clustering cases.
Thank you. And there was a question by Marius. He asked, did you consider using other clustering methods, such as expectation maximization with Gaussian mixture models or spectral clustering, or density-based spatial clustering, and go on. And if so, why have you discarded them?
So the answer for this question is pretty simple, because as I mentioned, the data comes from scientific presentation, and we used almost 200 of data. It's pretty small number of data to use some more complicated methods for the analysis. Now we are focusing on implementing some augmentation process to increase number of data, of samples to have ability to use those other methods.
Thank you. So a follow-up question, is the data available to public?
They are, and we are still working on publishing them. I mean that there are from scientific publications, so we need to check where we can and so on. Yeah, we're working on it, and we will notify the audience when it will be able, if there will be ability to use them.
This one is using two-dimensional shapes. And do you plan to consider 3D objects for the future work?
We are just on start of this investigation, so probably yes, but for now, with this clustering of 2D objects, we have results that can be applied in 3D. So we'll see.
Thank you.
Thank you.
Intersection of image processing with machine learning has great potential to solve many problems, and similar to this that has been done manually previously. Thank you again for this wonderful study. And thank you again, everybody, for being here. We could meet in the breakout rooms to continue discussing with the presenters. And each paper will have a dedicated room, and authors should join those rooms in the first place. And after that, we will continue with an important keynote speech on human-centered design of AI systems for frontline health by Professor Nihakumar. And see you there.